So after this long gap, we continue our lectures in string theory. We go on to the end of this semester and probably continue through next semester, provided you guys are interested. Okay, so in this semester, the things I want to talk about are the dates. Yes. What's the date today? Somebody know? Okay, so the plan for this semester is to discuss open strings. Let's continue with the bosonic string to start with. Open strings, to discuss toroidal compactifications and D-duality, D-branes, or one-loop amplitudes in string theory. We talk about oriented poles and so on. Yeah, this thing will go on for about 4 or 5 lectures, maybe 5 or 6 lectures. And we'll go on to discuss local physics on the world sheet of the string to derive the beta function equations on the world sheet of the string and to connect that with the equations of space-time, Einstein's equations. Discuss string theory curve space. That will be another 3 lectures or so. And so that's 8 to 9 lectures, maybe 10 lectures for all of this. And after which we will continue with to the discussion of the superstring. Okay? We'll try to do a sort of thorough discussion of perturbation theory with the superstring. We'll discuss what's called the RNS formalism, which is what's given in Bulchinski. But I was thinking we should also discuss Berkowitz formalism, which is a new thing developed since Bulchinski's book and seems to be proving increasingly useful. I don't understand that formalism yet, so that's motivation for us to discuss. Okay. That will probably take us through to the end of the semester. Then we'll see. If things go really well, by next semester we start trying to discuss space-time physics. So brane solutions, supersymmetry, space-time, and so on, and the API safety correspondence. Okay, fine. So now let's start. So our mission for now is to, if you remember last semester we discussed the bosonic string reasonably thoroughly. The closed bosonic string, we understood it in many ways. Okay? That's of course a toy model for most of real string theory, and we're going to stick with the toy model for some more time, just so as to avoid large complexities, as you will see when without being conceptually different, as you will see when we start studying superstring. But anyway, so let's stick with this for a while. Okay? So what we want to discuss is the open string. Okay. Now, what do I mean? If you remember, the way we started our lectures, 17 or 18 lectures ago or whatever, was to look at world sheets that propagated like that, with little cylinders that were propagating in time, and we tried to write down an action that described the propagation of these strings. But, you see, we assumed that the strings, and then we did a lot of work. But we assumed that the strings we looked at were these little loops that went propagating around. Now, you might ask, are there any other possibilities? Now that we've done all the work, we've understood the local physics and the world sheet of the string very well, we might wonder whether the same local physics might describe other motions. Okay? And the natural thing to wonder about, if you've got a bit of string, many things you can do, sort of if you think in space-time, but intrinsically, what you can do, there's basically 2 things. You can keep it open, closed. So we've discussed closed strings so far. Now you might wonder what's the story with open strings. So could we discuss strings that are little lines rather than little loops and understand their propagation in space? So that's the question we're going to address. Okay. So what we're going to assume, much of our analysis has been local on the world sheet of the string. Okay? And so suppose you've got a world sheet like this or a world sheet like this, we take a little local branch. Yeah, it doesn't care. It doesn't know the difference. So all that was local on the world sheet of the string will carry through. So all we have to do is to worry about new effects coming from the fact that we have boundaries. Okay? So let's start in a lowbrow way. Let's start as if we were starting with the first lecture for closed strings. Okay? And try to progress from there. So you remember that the way we tried to quantize, what was our basic action? We had 1 over 4 pi alpha prime, minus somewhere writing it, square root g times g alpha beta del alpha x mu delta x mu. Okay? And then in both our initial lowbrow as well as our more sophisticated ways of working with this action, we effectively fixed a gauge in which this G was some standard metric. And if we were working with the cylinder, it's just a flat metric with the theta coordinate periodic, with periodicity 2 pi and the tau coordinate 20. And then we worked with that metric for much of what we were doing. Okay? So now what we're going to try to do is the following. We're going to try to see if we can, again, once again fix a gauge, we keep G to be the flat metric in a space parameterized by by sigma and tau, but sigma will run from 0 to pi instead of 2 pi, and we will not impose a periodicity on the string. It will not be a closed vector, just be a strip. Tau runs up here. Okay? Now, having said that we're not going to impose periodicity on the string, in order to make it a well-defined dynamical system, we have to impose some boundary conditions at the edges of the string. So let's see how that goes. So the condition that we're going to impose, a well-defined dynamical system, the system from which you, well, if you take the action of the system and you vary the action, you get well-defined equations of motion. So let's see. Suppose you started with this action here, and you vary the action with respect to x. What do you get? Well, the usual procedure for getting equations of motions, it puts one delta on this x here, and then you integrate by parts. Okay? And the equations of motion are what's left once you throw away the surface term. Now that we've got a boundary of our space-time, we should worry about the surface term. So what's the boundary? What's the surface term? So the surface term is proportional to integral of it's del alpha square root g alpha beta x mu del beta x mu. Okay. Well, del x mu. Okay. Now, of course, this is the total derivative, so it can be integrated to something on the boundary. So what is it on the boundary? Well, we use Stokes' theorem, right? So it's the dot product of this vector with the normal to the boundary. Okay? So we can use Stokes' theorem and rewrite this as proportional to effectively this vector, whatever it is, dotted with the normal to the boundary. Now what's this vector? This vector is, let's move to flat space just to clear. Maybe that's what we're going to do. This vector is essentially delta x mu times del alpha of delta x mu. Okay? So this vector is supposed, let's call it T alpha. Okay? If we want the equations of motion follow from variation of the action, this vector on the boundary should give us 0. Okay, so that we can do this integration by parts to recover the equations of motion. Okay, now there are two natural ways to have this vector dotted with the boundary, dotted with the normal to the boundary give us 0. The first way is to impose the delta x mu equals. That is to say that x is some fixed value at the boundary. So the boundary conditions are that x is something fixed at the boundary. Okay, that will certainly do it, because the delta x mu will vanish. But there's a second way, and the second way is to demand that del alpha x mu dotted with the boundary normal is equal to 0. That will also do it for arbitrary fluctuation field delta x mu. Is this clear? Okay? Now these two things have names. The first boundary condition is called Dirichlet boundary condition, and the second boundary condition is called Neumann boundary conditions. Okay? The first guy is just saying that x can't change with boundary. The second guy is saying that the normal derivative of x at the boundary is 0. It's sort of like reflecting boundary conditions. Okay? Now, we'll continue this spirit of the earlier lectures and search for solutions to string theory that are Lorentz invariant. Okay, so in principle you could do something with x1, something else with x2 and so on. But let's to start with search for solutions to string theory that are full Lorentz invariants in 26 dimensions. So you achieve that by either choosing this boundary condition or this boundary condition for all 26 dimensions. Now let's see what will happen if you choose this boundary condition. If you choose this boundary condition for all 26 dimensions, you will have the zero mode of the string stuck near some place in both space and time. Right? Because the endpoints of the string will be stuck to some point in space-time. So maybe the middle of the string can fluctuate away a little bit, but not very far. This will not describe particle propagations. Particle lives at all times in time. Okay? As we go on with our study of string theory, we will find that actually this does describe something interesting. It describes an instanton in a path integral in string theory. It's what's called a d-instanton. But at the moment, we'll just discuss this. This is not what we want for now. So, the only Lorentz invariant boundary condition in what we discussed so far is to have this boundary condition imposed for all 26 dimensions of space. Space-time. Is this clear? Okay. So now let's take our boundary condition seriously and deal with it. So once again, we're working with this strip. We have sigma goes from 0 to pi. And we've got various fields x. So I'm going to now discuss the quantization of any given field x. So I'm going to ignore the label of x, the mu label on x. They all behave equivalently, as you know. So we've got some field x which is x of sigma, and we have that del sigma of x at 0 is equal to del sigma of x at pi is equal to 0. Okay. Now let's first solve this theory, and then I'll tell you about a convenient way of thinking of this that makes the open string look like half the closed string. Okay, but let's first, just very finished based on the theory. Okay, so what do we do? Well, we mode expand x into modes that obey the boundary conditions. Okay, so what are the modes that obey the boundary conditions? So they're essentially cosines. Okay? Cosine of n sigma obeys these boundary conditions. Well, it will be convenient to work with exponentials, so that let's write as e to the power. So we got x sigma is equal to sum over n. Okay, e to the power I n sigma plus e to the power minus I n sigma. Okay, this would be then let's put in a n. Okay, and I'll use some foresight to write numerical constants. So square root 2 by alpha prime. I'll put in a n, and I put in all possible time dependencies. So the only possible time dependencies that solve the equations of motion are e to the power plus minus I n sigma, I n tau. So I can just write it as e to the power I n tau and sum from minus infinity to infinity, not including 0. Okay, so far this is a classical solution, most general classical solution to the equation of motion. I should also deal with the 0 mode. So there's some x, some constant, plus some number. Let's call it q, and we change it to p with it. Okay, let me put the right. Again, use some foresight to put the right constant, and then we justify that constant. Okay, so this you're familiar with. We solve the equation del squared of x is equal to 0. This is the most general solution, so, which respect the right boundary conditions. As is clear. And I've not overcounted. You might have thought I should only sum from 1 to infinity because the cosine is the same. But I sort of put minus infinity as the negative time dependence. Same space dependence for different time. So this is really, they're all independent. Okay. Now this is all classical. quantum solution to this problem. So free theory, this classical solution determines the quantum solution. All we need to know is what the right so each of these ANs will be promoted. These ANs, this X and the P will be promoted to an operator. All we need to know is what the right commutation related to the operators. Okay? So let's work that out like we did for the closed string. Again, working in this slightly more sophisticated way than is usual, just because it's so convenient. Okay? So, like we did with the closed string, what we do is to work on the symplectic form on the space of classical solutions. Okay? So, the symplectic form is simply 1 by 2 pi alpha prime into delta of x dot wedge delta of x. Okay, integrated over sigma. Okay, what have I written? Delta x dot by 2 pi alpha prime is the momentum conjugate to x. So what I've written is delta of p of sigma where delta of x of sigma integrated over the world sheet of the string. Okay? And does everyone remember what this means? We discussed it when we discussed the closed string assignment. Do you remember what this means? This is a simple way of encoding commutation relations. Okay? So the coefficients. Okay, so a space that has omega alpha beta delta x alpha wedge delta x beta is a space whose commutators between x alpha and x beta are the inverse of this omega matrix, up to some factors of 2 and so on, that you'll find in your notes from last semester. Okay, so I'm just encoding the commutation relations, okay, in a simple fashion. And basically what I've done here is canonical quantization. The fact that the basic commutation relation is p commutator x as 1. I've written that in a fancy way. Okay? Now, this formal way is convenient because it allows you to change variables. So this is the symplectic form in the space of x fields. But we want the symplectic form in the space of a's, x and p. So all we do is take this general expansion here and plug it in. And that will give us the symplectic form in the space of a's, x's and p's. Okay? So let's move. So let's do the plugging in. So now firstly, you see, when we plug in, we get things that have particular sigma dependencies. And the integral from 0 to pi will kill the will give us 0 integral unless the sigma dependence is exactly cancelled. Okay, so because we've got cosine, and you integrate, you get sine of 0, sine of pi up with 0. Okay, so what we need is exact cancellation of these exponentials. Okay, so let's see how that's arranged. Firstly, of course, 0 mode can only click with a 0 mode. Okay, so let's work out first the 0 mode. So what do we get from here? X dot gets no contribution from x because there's no tau dependence. So x dot is 2 alpha prime integral delta p wedge delta x integral delta p wedge delta x. There's no delta p wedge delta p because that's 0, it's antisymmetric. So once we chose that to be delta p, the next one has to be delta x. And we have this integral, we had 2 pi alpha prime, and we have this integral d sigma. The integral sigma goes from 0 to pi, so we have 2 alpha prime divided by 2 pi alpha prime, which is equal to dp wedge dx. So this is the standard symplectic form between two variables that obey the commutation relation. X commutator p is equal to I. The I is going from classical to quantum. Okay? So Okay, this is what we started with in the field dp wedge dx. This is the standard. That's why I chose this to alpha prime. You know, so as to get this to be the standard. If I didn't know what to start with, I would put an arbitrary constant and chosen it to be the standard. Okay? Good. Now let's move on and do the oscillators. So for the oscillators, once again, you only have to worry about what you get when n's are either equal or opposite. But n's equal don't contribute because delta an with delta an is 0. This is antisymmetric. So you only have to worry about what you get when n's are opposite. Okay? So let's do that. So what do we get? So let's take delta x dot and act from here. So you get delta an. Okay? And then we need to dot this. So we get now both of these things have the same time dependence. So in times e to the power in sigma plus e to the power minus in sigma with a particular time dependence. Then we're going to multiply by a minus n, that has the reverse time dependence cancels. And so we get delta an wedge delta a minus n and e to the power in sigma plus e to the power in sigma. Okay? And this thing has to be integrated. This thing, the whole thing has a 2 pi alpha prime, and it has to be integrated over sigma. This integral is 2 pi. 2 over.
Which comes from that normalization.
Sorry. Oh, thank you. Square root that. There's a factor of 2 over alpha prime because we were clever about choosing our normalizations. You're right. So 2 over alpha. Should have been alpha prime over 2. Alpha prime over 2. We were so clever about it. Okay, so now what do we get? Let's do this integral. The integral gives us 2. This connects with this connects with this, yes. 2 pi. Okay? Or another way of saying it is that this is 2 cosine, that is 2 cosine, so it's 4 cos squared, cosine averages to half, so it's 2 times pi. Okay? So what do we get? We get 1 by 4 pi times 2 pi times d an wedge d a minus n times I times a. Okay? But this is what we got when we chose a in here, a in taking the dot, and minus a in the undotted guy. Sorry, n in taking the dot, an in taking in the guy where we took the dot, and a minus n where we didn't take the dot. There's also a term with the other guy. That term is also 2 pi by 4 pi into delta a minus n, where delta a n, but with a minus I, because you just replace n by minus n. It's exactly the same thing, right? But that's good because this thing is antisymmetric. So when we put this back here, that cancels the next thing. Okay? So the next symplectic form is gets rid of this half. So it's sum over n delta an with delta a minus n with an I times n. Oh, and we should have been even cleverer in choosing our expansion. We should have been putting in. Sorry, people. It's just you want to stick to. If you want to stick to standard string theory conventions. Sorry.
That was the expansion of
delta of x.
Delta x, exactly. Standard string theory convention, we expand with an n. So this whole thing comes with a 1. N here, N here, and now this. Okay? And now I'm going to leave it for as an exercise for you to check. You see, basic. What is this symplectic form? It's clear that it's that up to this factor of n and up to some possible minus signs, it's the symplectic form between the creation and annihilation operator of a harmonic oscillator. Right, if you just had delta p with delta x, you get x commutator p is I. Now we've got an extra factor of I, so we get an commutator. If we didn't have this n, we would get an commutator a minus n is 1 plus minus 1. Okay? No, with the n is downstairs. So when we invert omega to get the commutation relation, it will go upstairs. Okay? So it's clear immediately without doing any check that we get an a minus n is equal to plus minus n. The painful thing is to work out plus minus, and I'm going to ask you to check that it's plus. Actually, we could probably do that in our heads. Right. The way to do it in our heads is that I goes down. You know, what we're going to get is I times n by I. You see, instead of n, we get n by I. Right? And then other than that, we get the. Yeah. Anyway, I'm going to ask you to check that.
There's no n equal to 0 part.
There's no n equal to 0 part. We've taken on the 0 mode expression. N runs from minus infinity to infinity, excluding 0.
In the x and p combinator, there will be I equaling pi.
Pi?
Pi will be cancelled.
No. I mean, it's the integral over sigma.
Oh, I see.
That gives us. Okay, you do this correctly, and you get an commutator a minus n is equal to 10. Okay, so now we've completed the quantization of our system. This expansion that we wrote down is the correct quantum mechanical expansion for the operator x of sigma, where an's, x's, and p's are operators that obey the commutation relations we just derived. What are the commutation relations? An's with positive n's are annihilation operators, an's with negative n's are creation operators, and annihilation and creation operators. So we've got an infinite number of harmonic oscillators, plus we've got the 0 mode. The quantization 0 mode is a Schrodinger wave function of a freely moving particle. Okay, and quantization of the harmonic oscillators gives us harmonic oscillators. Okay, this is exactly the same structure as the closed string, with one important distinction. Notice that while the closed string had two sets of harmonic oscillators, we only have one set of harmonic oscillators. What's the physical reason? The physical reason is that our boundary conditions tell us that what's going left bounces back and comes forward and right. So left movers and right movers are independent degrees of freedom. They're the same degree of freedom. You know what's happening to the left mover, you know what's happening to the right. Okay? So, the 0 mode structure has not changed significantly. It has changed in one detail. Can anyone tell me what is the difference between this expansion for the 0 modes for the open string and closed string? There's just one number. If we want to expand momentum conjugate, what would this number have? Well, if you look up your notes, it will be 1. Can you tell me why it will be 1? Exactly. The integral goes from 0 to 2 pi. So they get the same. So the 0 mode structure has changed in one number. Okay? But otherwise it's the same. There's only one 0 mode both for the open strings and the closed strings. But the oscillators are double in the closed string. Okay, you've got a left moving oscillator, right moving oscillator, open string, just the one set of oscillators. Okay. Now that we understand this, What? No, it will make a difference in the mass once we start computing because momentum is what becomes del by del x wave function. So it's important. This is the right thing that preserves the xp commutative relationship. Okay. Now, before we're soon going to go on to talk about what this means in space-time. You know what spectrum we get of the open string space-time. But before doing that, let me tell you about a little trick that people find very useful all the time. And that little trick is what's called the doubling trick. Okay. And the basis of the doubling trick is a very simple observation. It says consider any function y which is defined from 0 to 2, defined from 0 to 2 pi. It's a periodic function. Y is a periodic function defined from 0 to 2 pi. Okay? Periodic. Now, let's define an auxiliary function starting with y, which we call x, as follows. Where x is defined in x, we define sigma in the range 0 to pi. Okay? Now, y is a periodic function from 0 to 2 pi. Let's see what this x, what boundary conditions this x satisfies at its boundaries. Okay? That's very simple because del x is simply equal to del y at sigma minus del y at 2 pi. Minus because of this minus sign in there. So the function del y evaluated at 2 pi. Okay? But y and del y are periodic functions. You know, so and if you set sigma equals either 0 or pi, this becomes so equal to 0, that sigma equals 0 or pi. Right? Because you just get the function del y at 0 minus the function del y at 2 pi. If you set sigma equals 0, which is the same as, which is 0. Similarly for pi. Okay? So, we have this nice trick. The space of functions that are defined with these Neumann boundary conditions from 0 to pi is the same as the space of periodic functions. Okay? Yeah, no, that's okay. That's not quite true. There's a map from the space of some functions from 0 to pi to the functions on the line. This will not be a one-to-one map. Basically, it's halving. There will be different functions here. Okay, which will not be important for us. But sorry. So the accurate statement is that this map from the space of periodic functions in 0 to 2 pi. Okay, to the functions on 0 to pi with the boundary conditions that we're interested in. Okay, now the next thing we're going to do is to ask, let's see if there is a y function for our solutions. Okay, is there some nice y function defined in 0 to 2 pi? Again, that is nice and periodic, that maps to our solutions. Okay? And I want to claim that the answer is yes, and that this y function is.
So this map, for any x we can find a y, but it won't be unique. Is that what we are looking at?
That's right. Yeah, there will be different y's that give us the same things, but we won't bother. We're not going to use this in any way except for convenience. This is going to be a mathematical trick that will be useful. So for the x's that we're considering, we will find a y. Okay, that does what we want, and this will be all that will be important for us.
Yeah, but any x that is.
Yes, for any x is y. We've just written down the most general x that satisfies this probability, and we find a y for it. So that will demonstrate. Okay, now I want to claim that the right y function, that y of z, is equal to alpha prime by 2 sum n is equal to minus infinity to infinity, again excluding 0, a n e to the power I n tau plus sigma. Okay, and then say plus x plus 2 alpha prime 1 over. Okay, why is this correct? This is correct basically because if I replace this by 2 pi minus sigma, the 2 pi doesn't do anything because it's
The alpha.
where? No. This part is not affected by it. This is not a function of sigma. Okay, this whole doubling trick will only be useful for the oscillators. You see, this is not a canonical quantization. Yeah, it's only.
Okay, then we are defining x as y plus y sigma y to minus sigma by 2.
Oh, good. We probably want to by. No, we don't want by 2. So we were just saying this should be divided by 2. Yeah, probably. Yeah. Okay. So thank you. Okay. So why do we get this? It's because the rule says that we should add y of 2 pi minus sigma, but the 2 pi doesn't do anything because of the n here. So it's just y of minus sigma, which is this. So it's manifest that this guy, which is this guy, under this map. Right? I'll emphasize that this is a mathematical trick. You might think this is an unmotivated thing to do, but it's a mathematical trick that will prove useful in any context, though it will only prove useful for the oscillators. Okay? So we'll see what goes. Okay. Now, you see, the key point is the following. The quantization that we achieved of our system is exactly the quantization you would get for this expansion of y from the closed string for the oscillators, not for the zeros. If you remember, for the closed string, what we had was a left moving sector and a right moving sector that didn't talk to each other. There was a level matching condition, but we've not yet got to the point of imposing constraints. We're just working out the quantization of this worldsheet. Okay? So the left movers and the right movers didn't talk to each other. The quantization, we have quantization of a n and a minus n within left movers, and a n tilde and a minus n tilde within right movers. And we had exactly this expansion for the left movers to get the standard commutation relations. Okay? So, suppose we formally thought of the action as being a closed string, like a periodic closed string, but we're expanding solutions with only left movers. We would get exactly the same quantization. Okay? As for the open string. Okay? Now we're going to, in successive steps, we'll use this observation again and again and again. It's a mathematical trick, but sometimes a little slippery in your mind. But it's very useful. So we'll use it again and again and again. So keep again. Fine. Now let's use this to okay. Now there's one more thing. So far we've only been discussing these x's. But let's talk also about the stress tensor. Okay. So remember, of course, that there were two important stress tensors in the game. There was okay, so there were two important stress tensors in the game. There was T++ and T minus minus. T plus minus was just, it's the stress tensor. Okay, now remember that T++ was proportional to del plus x, and T minus minus was proportional to del minus x, del minus x. Okay, so now let's look at this in a little more detail. You see, let's look at what the boundary conditions imposed that the x fields have on boundaries, what that implies for the boundary conditions on T++ and T minus minus. Okay?
Okay, so before going to that, like all the other, the definition of plus and minus are all the same.
All the same. It's plus is tau plus sigma, minus is tau x. Okay? Now, the condition that we had in the boundaries was del sigma of x is equal to 0. Del sigma is proportional to del plus minus del minus. Okay? So, in terms of plus minus, the boundary condition is the same as saying del plus x is equal to del minus x. At the boundaries. The boundaries. Okay? So, multiply again by del plus x and del minus x. We get the condition that T++ at 0 is equal to T minus minus at 0. And T++ at pi is equal to T minus minus at pi. Okay? So this thing tempts us to define a T. Again, formula trick. A T++, extended, which is equal to T++ of sigma when sigma belongs to 0 and pi, and is equal to T minus minus, what is it, 2 pi times sigma, when sigma belongs to pi 2. Yeah, pi to 2 pi. Okay, now it's very similar thing to this x and y. I'm going to leave, it's a simple algebraic exercise, and I'll leave it to you to check that with this definition, T tilde plus plus is simply equal to del plus y. Maybe there's some by 2's. By 2's, okay.
Actually, even there's one over 2 by alpha prime which is
yeah. So whatever is the constant, exactly. So let's not keep track of the constants. Modulo some overall constant out of that. Okay, we're just going to get del plus y, del plus y. Okay, so please work on the constants. Yeah, this is all. Okay, that frees me of the burden of keeping track. Okay. Okay, good. So you see that this doubling trick has a counterpart for the stress tensor. What were we supposed to do in canonical quantization? We were supposed to impose both T++ equals 0 and T minus minus equals 0 at every point on the string. Okay? But what we are saying is that in Now, the great thing is that this reduces to a problem that we've already solved before. Yeah, why is t plus 0? Remember, so this is the old logic. Remember, we started off with an action that had both stress tensor as well as x. Okay, then we fixed gauge to set the stress tensor to be this conformal gauge.
Yeah, the G.
But there are the G equations that you impose. One of them was automatic, stress, but t plus and t minus minus had to be imposed. And that's how we first did our quantization. We started with the same thing for the open string. Okay? So that requires us to pointwise set t plus and t minus minus equal to 0 from 0 to pi. But that's the same thing as setting t plus tilde equals 0 on the whole circle. But you remember what we did when we quantized the closed string? We set both t plus and t minus minus to 0 on the whole circle. But t plus cared only about the x plus part. So this is exactly the same thing as a quantization of the closed string. Because now we've got an expansion in terms of which we've got the same commutation relations as 1/2 the closed string and the same constraints as 1/2 the closed string. Apart from the 0. Right. Okay? So, exactly. So now let's deal with that additional factor of 2. So the only complication is that additional factor of 2. Okay. So now let me remind you what we got when we quantized the closed string. Okay. What we got, of course, you remember the first way we did was, and let's repeat that for a moment, we did a light cone gauge. So we set two of the transverse fluctuations times one spatial coordinate to 0, but then we still had to impose L0 equals 0. Okay? And the L0 equals 0 condition gave us that it was actually yeah. We got alpha in the closed when we worked on the closed string, we got alpha prime p squared by 4 plus sum of n is equal to 1 to infinity alpha minus n alpha n. And now I'll replace all the which x in this is. Okay, so this is the full vector p mu squared and I squared, and then we got this equal to d minus 2 over 20. I'm not going to derive this again because we did this in great detail. You have this in your notes. You have your notes. Okay, okay. So, and you remember that we had various ways of understanding that d had to be equal to 26. Okay. So let's just see what changes. The only thing that changes here is that p is replaced by 2. As we've seen. So this becomes alpha prime p squared plus this. Because the 0 mode expansion was different by that factor. Okay? So this, the full quantization of the open string, including all constraints, gives us 1/2 of the closed string. Okay? With this one change. Now, if we wanted to, we could go through the logic. Let's examine the spectrum. Okay. Of course, we have 20,000 ways of seeing that d is equal to 26. But we had one nice way of seeing just the light cone gauge. Can anyone remind me what that way was of seeing the light cone gauge when we did closed strings?
You just look at the first move.
Huh?
That. Okay, first see that it has some gauging values and then check that.
But why does it have gauge in there then?
Because you can. Okay.
Let's do light cone. The thing you're talking about is canonical codec.
So,
It's the covariant.
Okay, like cone, you have to evaluate the reverse completely.
Okay, that's one way of doing it. Just the level of spectrum, there's something easier.
so we had this tachyon, and at the first level we had to mask this particle, and that had to be a particular representation of the middle group, and that.
Very good. So what Jyotirma is saying is that at the first level, there are d minus 2 particles with that energy. So this has to be in the right rep. If we're maintaining Lorentz invariance, it has to be in the representation of the little group of the theory that is d minus 2 dimensional. But there is no representation of SO d minus 1 that is d minus 2 dimensional.
Unless you are looking at the
But there is a representation of SO d minus 2 that is d minus 2 dimensional, namely the vector. Okay? All particles have to transform in representations of the little group if you maintain Lorentz invariance. Now there are two options. Either the particle is massless or it's massive. It could be tachyonic, but that's not going to change. Okay? So either, if it's massive, it has to transform in a representation d minus 1, SO d minus 1. But there's no representation of SO d minus 1 that is d minus 2 dimensional. So it can't be massive. So the only way it could be consistent is if it's massless. Okay? But it's massless if this is equal to 1. Okay? So d is 26. So we'll replace it. Okay? Now, so we have the same logic for the open string. Actually, in the closed string it was more complicated because we have to take the thing from the left and the thing from the right. So this is the logic that I expect. That was really the logic for the open string. And it's massless. So what is our spectrum? So at lowest level we've got a tachyon when this is 0. M squared is equal to minus 1 by m. P squared is minus n squared. Okay? Next up we've got a gauge mode. Because it's a massless vector field. The only way to make a consistent theory for massless vector is the gauge mode. And then at high levels we've got whatever you've got. Can somebody remind me why this problem of having representations of SO d minus 1 rather than d minus 2 does not affect the second excited state? Now it looks like everything is in representations of SO d minus 2, right? But why d minus 2 by the way? Because the I in this case in light cone quantization run from 1 to d minus 2. Okay, so why doesn't this argument also tell us that the second excited state has to be massless? Which of course would be a contradiction. It couldn't be the first and second of both of those. So it's good we're doing the open string now because this is a review of everything we did for the closed string. So can you list all the particles that appear at this level? Help me. What are we getting? I think standard notation is called alphas. I've called it A's, but they call alphas. Yeah, okay. Tell me.
So
at the next level, at level 2.
At the level 2.
Yes.
Okay.
What do we get?
So you get alpha I and alpha G.
Alpha I, alpha J. What should I put here? Minus n. I want level 2.
Oh, you
Minus is raising, so that's okay. But you don't want to raise it so much.
There can be a -1.
Shall we have exams in this course? Maybe it's worth it. Let's have an exam in this course. Okay, I'm going to set an exam, a midterm exam in prepare tomorrow, which will examine you in everything you learn for close to theory plus whatever we learn. This you should remember. Come, this is -1 and -1. How else to make up 2? That's one way. Acting on the vacuum.
There will be a alpha -2.
Alpha -2. I acting on the vacuum. Now, can somebody? This thing is a representation of SOD -2. What representation? And describe it in words.
Symmetric and
Symmetric tensor. Let's just call it the symmetric tensor. This thing is what representation? Vector. What can you build a representation of SOD -1 by combining these two? It's symmetric traceless tensor of SOD minus 1. Okay? Of SOD minus 1. See, you've got a symmetric tensor of SOD minus 1. We'll decompose it into D minus 2. And so symmetric and traceless. So because it's traceless, let's say that we can effectively get rid of this integrand. We get this vector, same as this vector. This is one vector. And then we've got a full symmetric tensor that's not necessarily traceless. Alright? So this is the state content of a representation of SOD minus 1. So it's possible that things group together into representations of SOD minus 1. You work this out at higher levels, you find the same miracle happens. At every level. And then there's formal proof that it works. Okay? So it's only at level 1, but there's only one state. So it could combine together with something else to form a representation of SOD minus 1. D minus 1. At every higher level, there are many kinds of things that can combine together. Okay? Good. So fine. So we have this all working nicely. The only thing that's changed is that we don't have to tensor the left movers and the right movers. So at level 1, we genuinely have a range bosons. What do we have at level 1 from in the closed string? Only the gravitons? We have the gravitons, that's correct. But what else? The tachyon was not at level 1, it was at level 0. What else do we have at level 1? What? Very good. B union. The antisymmetric die. And the phi. The dilaton. The dilaton, the antisymmetric B, and the graviton. How do you see that? Well, it's whatever you get by taking a vector times a vector. So that's symmetric traceless, antisymmetric, and the trace. Okay? Here things are simpler. You don't have to take anything times anything, it's whatever you get. Just the gauge. Very good. Okay? And you can work out when you get higher and higher levels. Fantastic. Okay. So that's it. We've completed our canonical quantization of the open string and light cone gauge. And we've understood already a lot of physics. And the lot of physics that we've understood is that in the same sense that the closed string gave us gravitons interacted with many other things, the open string gives us gauge bosons interacted with many other things. You know, and of course lots of massive stuff. And there's always this irritating tachyon that we don't know what to do with, but we'll go away more sophisticated constructions and may or may not be physical. There was a talk in this year's strings conference trying to claim that they understood the main point of this tachyon condensation. Not sure it's entirely conclusive, but it was interesting. And let's try. Okay, so great. So now you remember what else did we do for open strings? The next thing we did when we were trying to understand open strings was to understand this quantization in a more sophisticated manner. Okay, well, we did two things. We first understood the worldsheet theory of the string in a more sophisticated manner, language of conformity theory, and then we understood the quantization of the string, this integration over metrics, in a more sophisticated manner. Okay, let's follow that path. So, the first thing that we did in trying to understand things in conform. So, our first goal is now to try to understand the worldsheet theory of the open string slightly more sophisticated. Okay, we'll understand the Euclidean space like we did with the closed string. Okay, so the first thing that we did was to remind ourselves that we analytically continued Euclidean space. And then made a conformal transformation from the cylinder to the plane. We're going to do the same thing. We're going to analytically consider the Euclidean space and make a conformal transformation from the strip to whatever we get. So how do we decide what we get? Well, let's remind ourselves of that and what the continuum is. Omega, which is equal to sigma 1 plus I sigma 2. These were the coordinates of the strip. Sigma 2 is I times tau. Okay? And then we define z is equal to e to the power minus I1. Okay? Which read in terms of sigma 1 and sigma 2 is e to the power minus I sigma 1 plus sigma 2. Okay? So you remember that what that did was to take lines of constant time on the cylinder were constant circles on the Z. Okay? The size of the circle was decided by what time? T equals infinity was the infinite size circle, T equals minus infinity was the origin, 0 size circle, T equals 0 was the unit circle. Okay, now what are we going to get? So let's look at how this, all that was correct when sigma ran from 0 to 2 pi. But now sigma runs from 0 to pi. So we get the same picture as before Z, except that we have not jumped the whole plane but the half plane. The origin, lines of constant sigma 2 are circles, that are ever bigger or smaller, and all of this action is happening on the half plane. This is the Z half plane. Okay? Now, let's rewrite our expansion of x, the one that we had at the beginning of this board, in terms of z. Keep your wits about you to get the i's right. Better here. That. There's okay. Okay. So what we're supposed to do is to take the expansion that we had in terms of W, make the analytic continuation on tau. So tau goes to, how does it go? I sigma minus, the way that you always analytically continue in an action. Okay? And then replace. So the thing that was e to the power I tau minus plus sigma will go to some analytic combination of tau and sigma, and then under this map, okay, will map to some power of z. Is this clear? So that's going to give you this, and then the other one will give you the center. Okay, so this is just a rewriting of the same thing that we had. Okay, in terms of these new z and these new z variables, we had exactly the same rewriting, for the closed string, except that for the closed string, the coefficient of this guy and the coefficient of this guy were independent. Here, they're the same. H. Where is H? 11. This is tau. It's a fancy way of writing 2 tau. Okay? Now, okay, so we've got this nice expansion of x in terms of these analytic coordinates. But what about y? We also have this. P, yes, that's right. I here? Yeah, this I confused. Let me see, let me just check. maybe there was an I in the previous expansion. Sorry, I think maybe that's the sorry. Okay, there is an I here because Wilczynski has it. But where could it have come from unless there was an I? So I think the whole previous expansion should have had an I. Now the way to check that is to check whether the commutation relations I claimed. What?
I think we got to that.
Let me check that on the fly since there's some. Sorry, so let's back up. Okay, so we had an expansion which had alpha prime by 2. We started with no I. Okay, alpha prime by 2. Then we had alpha n by n. And we had e to the power I n sigma plus e to the power minus I n sigma times e to the power n. Okay. Now, when we work this out, what do we get? So let's do that really carefully. We get I n. Okay, so the I is in the numerator. That's the really important thing, right? So we get d alpha n weight d alpha minus n into I by n. This is what we got. Now, the standard guy is dp wedge dx. Okay, so this tells us that alpha minus n commutator alpha n is equal to I divided by n by n. So we got the wrong one. You see, when you have dp wedge dx, you have x commutator p is equal to. How about?
This I've got there d alpha minus n with d alpha.
Here you got d alpha minus n with d alpha n. Let's check that. We had dx dot with integral dx dot wedge dx.
Yes.
Okay? So we get, if we take alpha n from here, we'll get a plus I n.
Yes. You get a plus I n.
So we get d alpha n wedge d alpha minus n.
But then you get a minus 1 by n.
With
Alpha
the
minus n. So you get plus I n into
oh. No, but we always dividing by
it's plus I n by n into minus 1 by n.
oh, right. Okay, you're right. This makes complete sense. Yeah, so where did the I come from? We have, no, wait, let's take this through. That's probably, no, you know, oh, wait. You know the way yeah, I think the I is from the fact that, okay, we have to be careful, right? Because so what's the right way to transform x from one side to the other? You don't transform x, you transform del x. Because del x is a good conformal operator.
Yes.
Now del x is a conformal operator of weight 1. Okay? So the transformation property, the transformation rule that takes you from x of w, okay, to x of that has an I in it. That's the key. You see. Yeah. Let me clear this. The transformation basically. Remember that's taken out of derivative. Okay, I'm okay, let me try to clear up this I for next class. Well, okay. We probably did it correctly for the closed string. If you look up your notes there, we probably had the I's correctly there. It's the same story, but I'll look it up and clear that up for next class. Sorry. That's not I mismentioned. It's probably the right basis which is yes. Okay. Actually, since maybe I will. Okay, anyway, let me clear this up next class. That's some I agree with you. It's a mysterious argument. Okay. It may be related to. Okay, let me just try. Okay. So let's just forgive this I for the moment. We'll keep it there since Kuczynski has it. It's probably correct. Okay, and move on. Okay, so it may have to do with the translation between x of w and x of z. That may be somehow the heart. It's a little fishy, but let me. Okay. So the next thing that we want to do is to try to understand what the analog of this y field is. Okay. What the analog of this y field was on the z plane. Now you remember the way we got this y field was that we just took the left moving part of x was all of y between 0 and pi, and the right moving part of x was all of y, okay, between pi and 2 pi. Okay? So, what does that correspond to here? That corresponds to saying that y is a function. Firstly, y was defined from 0 to 2 pi, so it's defined now the whole complex set. Okay? And it corresponds to saying that y of z is equal to x of z in the upper half plane. By x of z, I mean the analytic part of x of z. Because that's how it works. Remember? It's just left moving part in from 0 to 2 pi. But the right moving part on the other part, okay, is equal to x of z part in the lower half. Right, so this has to be how does this have to go? This will be sorry, what about the one? So, right. X of z bar in the lower. So y of z at the corresponding at what corresponding point? At z star, right? So you just want to change the basically star. Okay. So suppose I want to find what y of z is at some point in the lower. Okay. So I want y of z. So I take z and star it. That gives me some object z, and then I evaluate x and z. Again, that's an analytic function of z bar. That's this object. Okay, this is the same thing as this reflection from this 2 pi minus sigma in the z coordinate.
Yeah, so can you say that this x of z, you basically don't drop that one by z?
Yeah. So it's this term above and this term below, but it's this term, not, so suppose we're interested in what our field is here, we take the anti-analytic part of what it was there. See, what do we do on the strip? if we wanted what the y field was here, it was left moving part. But what the y field was here was the right moving part at the corresponding point here. 2 pi minus sigma, right? So we're doing the same thing here. We're saying if we're interested in what the y field is here, it's the analytic part. Okay? If we're interested in what the y field is here, okay, it's the anti-analytic part, but at the corresponding reflected point, where the imaginary part is reflected. Okay. Now, the fact that we had this nice periodic function in y when we did that before, okay, translates to the fact that this is just some nice, well-behaved analytic function on this whole plane. Okay, it's basically the fact, you would have to check that derivatives here match, but they do from the boundary conditions. It's basically the boundary conditions of the bounded word. Remember, del plus is equal to del minus, okay, which is del z is equal to del z bar at the boundary, right? Because del z of x is equal to del z bar of x, which tells you that this way of doing it gives you matching derivatives at the boundary. This is say etc.
And the zero mode will give a branch curve.
Yeah, the zero mode is going to be a free right? So
So it will be log z.
yeah, yes.
So
So really, this will be useful only for the field del y.
yes, then it's all.
Then it's all. As usual when we deal with the formal field theory, the field x or the field y is not a good field, but the field del x is. So we never use these tricks for the zero. The zero mode doesn't. This trick doesn't do anything nice with zero, but it does for all the oscillators. A clear way to separate the oscillators from the zero mode is take a benefit. Okay. So this nice doubling trick that we described at the level of this field of the cylinder and the strip becomes even nicer than the It's the same thing. Defined from 0 to 2 pi means defined on the whole complex length. It's just translating that into this language. It's the same thing. Okay? But it's very nice. Okay? All the conformal field theory tricks that we played, when analyzing the closed string, go through for the analysis of the open string when we use this double field y. Okay? So in particular, for instance, yeah. So what are the various things that we should do? I'm going to suggest you 3 exercises. Okay, the first exercise is to compute the commutation relation between alpha m and alpha a using the formula. What do I mean by that? Write down, in terms of the field y, write down a contour integral expression for alpha m. Okay? And then use the OP, the usual OP between x and x, okay, to compute the commutation relations in the way that we did it 20,000 times in the previous class. Okay? I want each of you to do this exercise for next time, just to remind ourselves of all these techniques. It's the same thing as for the open string, but please do it. It'll also help check whether this I is correct. It's directly in Z space. Okay? So please do this. Okay. Secondly, compute the commutation relations between T and T. Oh, I mean, LM and LM. So, do the usual expansion of T of Z is equal to sum over Lm by Z to pi 2 plus 2. Okay? And once again, compute the commutation relations between Lm and Ln using this, using the, okay, of course the TTOP remains unchanged. because the same expression takes in terms of fields. Using that, compute combination between T between LM and LN. What I'm asking you to do is to just repeat everything you did for the closed string. It's the same exercise, just identical. Okay, but I'm asking you to do it anyway, just to remind yourselves of that. So please, for the next class, just do these exercises. Okay, and lastly, how does the state operator work? Okay, so see, how does it work for closed strings? So first let's work in the W plane, the physical W plane before we do that. Okay, how does it work for closed strings? Closed strings we had this whole circle. The whole circle, boundary conditions in that circle, for the path integral in that circle define the state. Now we can use scaling to shrink this thing and just to make it as small as we wanted. That defined an operator insertion into our field. Okay. How will we work? How does it work here? Okay. Here, how does it work? It works once again with our state here. We shrink it and we get as near to this point as we want. What do we get? We get an operator insertion at the boundary of our worksheet. Is this clear? Okay? Is this clear? Let me just remind you about the closed string discussion. In that situation, state was defined by the boundary condition of the path integral here. But by scaling, we could shrink that to as small a circle as we wanted, and then effectively there was a local insertion somewhere in the worksheet. It happened to be the origin, but the origin was not a special point. It's like any other point. Once you know how to define an insertion at any point, you know how to define it everywhere. This is the local operator. Okay. So I have to find a local operator somewhere in the bulk of a worksheet. Now, however, how does it work for the open string? Okay? So for the open string, it works as follows. A state, where is a state defined? A state is defined on lines of constant tau in W. Right? Which was some semicircle. This is where we give up our boundary conditions for the path integral defined state. Scaling brings it down here. So we get some local insertion at a point. Now this point is nothing special in the sense that you can move it anywhere along the boundary. But clearly you can't move it to the bulk. So boundary point is different from a bulk point. Okay? So the state operator map for open strings establishes an isomorphism between operators that you can write down on the boundary of the worksheet and states on the string. Is this clear? Okay? Now, how are operators on the boundary of the worksheet different from operators in the bulk? Okay, you see, what were the operators in this X theory? What were the operators on the in the bulk? Effectively, what you had was any number of holomorphic derivatives on X, or any number of anti-holomorphic derivatives on X, times e to the power k. These were the set of operators. Okay? Now, on the boundary, you have fewer. Why? Yes, what are the boundary conditions? Del sigma of x. Now, what that becomes z and minus z bar? Del z x is del z bar x. So, suppose you try to insert del z bar to the power n of x. That's the same thing as inserting del z. various derivatives you can put on z, z derivatives you can put, and products thereof. And what is the most general operator? We could have had del z to the power n1 of x times a n1 times all power to whatever power times del z bar. Okay. Remember how the state operator map worked. Del z to the power n1 and x mapped to a n1. The holomorphic a minus n1 acting on the vacuum. This operator mapped to a minus n1 acting a n1 times. Should have used a different symbol. Okay? The fact that you can have products of both holomorphic derivatives of x and anti-holomorphic derivatives of x told you you have the Fock space of both left movers and right movers. That was how the state operator map worked for the closed group. Now, however, you don't have two sets of derivatives of x you can put, you only have holomorphic derivatives or anti-holomorphic. That's the difference. Okay? And that maps to the fact that on the strip we have only one set of oscillators. Let's call them holomorphic. Because good for them, anti-holomorphic. Okay? So my third exercise for you is to work this out in detail. Okay? So what I want you to do is to repeat the arguments that we had for closed strip. Namely, if you remember, the way we worked was to say, suppose for the closed string we had the insertion of del z to the power n in x, yeah? And then we worked out what state that corresponded to. How did we work it out? We worked it out by surrounding it by some a operator and finding what we got when we acted by a. And that completely determined it. Okay? So work this out again for the open string. Okay, you can work it out either the y language or the x language, but somehow work it out and find this isomorphism once again. I just spelled out the answer, you know what you're going to get, but work that out to your own satisfaction, and if there's something confusing, comment on to me. Is this clear? Okay? So, all the conformity theory, I've only, by the way, reviewed the parts of the conformity theory discussion we had. If you remember, we went through this in 5 or 6 lectures. It was a long story. I only reviewed the parts that are different from the open string. Okay. Anything that, for instance, involved deriving an equation of motion and what that meant inside the path integral of Noether's currents. So all these are local properties of the string world-shape path integral, and they don't change at all. The only thing that we've discussed is how having boundaries changes things. Okay? So that ends my brief review of effectively chapters 1 and 2 of Kolchinsky, the paths involving the open string. Okay, let's quickly go on to chapter whatever it is. It's 3. The paths involving the open string, chapter 3 of Kolchinsky. Okay? So that's the part about honest quantization of the string. That was chapter 4. So chapter 3 is called the Polyakov path integral. This is the thing. Chapter 4 is string spectrum. Maybe we have different editions.
I have you read out the spectrum.
No. What I want to do is to set up the path integral. I want to understand what happens to BC ghosts when we have okay. So again, we're not going to do that whole quantization procedure. Okay, we've done it. But just remind ourselves about the elements that are necessary to understand what we, what we want. So what was the element that, what did we have? We had G alpha beta, some world sheet metric, and we had X infinity. And then we went to some conformity. So we said G alpha beta is equal to some diffusion metric, for instance, eta alpha. But some G hat alpha beta times e to the power phi. We used diffeomorphism invariance to do that. And then we worked out what the Faddeev-Popov determinant for this gauge fixing was. Now you remember how we worked that. We said up to, well, how does a diffeomorphism change? How does a diffeomorphism change G tilde? How does the diffeomorphism change that? So what is the Farley-Popov determinant? So you're supposed to look at the variation of your gauge condition. Again, compute the determinant of that. Our gauge condition was that G was equal to this. So we have to look at the variation of this under our symmetric transformation. So the variation of that was del alpha V beta plus del beta V alpha. This was under diffeomorphism, but then we added a conformal transformation that made this traceless, because the other part was trivial. Okay, so divided by 2 minus del V G hat alpha beta by 2. Okay, so this was diffeomorphism plus this plus particular conformal transformation. I don't want the 2 in the second term, but let's take the trace. I do, right? Because this trace is 2. I would have been by D generally. These 2. Okay. Yeah. So we had this change, and then the Farley-Popov determinant was generated by replacing B by a harmonic variable and replacing the vector delta function parameter. So we had a B alpha times del alpha C beta del beta C alpha by 2 minus delta C by 2. Okay, this was the alpha. Though it turned out to be most convenient to write these, the B with the lower indices and the C with an upper index. When we did that, it was in a local analytic patch. This action always reduced to B del bar C plus B bar del C bar. Okay? Yeah. Now, the basic thing that I want to remind you of was the origin of these C's and these B's. The C was simply the infinitesimal diffeomorphism parameter converted into an anti-kinetic field, and